Thank you very much to the Econophysics Colloquium 2022 for the invitation. Hello everyone, my name is Alejandro Rodríguez Domínguez and I'm going to present my work on portfolio optimization based on neural network sensitivities from asset dynamics with respect to common drivers. Since Markovich in 1952, portfolio optimization has been understood as the following quadratic optimization problem. In figure 1, we can see the efficient frontier and the tangency portfolio as the intersection with the critical allocation line as the solution to the optimization in 1. It also introduces the concept of diversification and how we can reach similar return levels with less amount of risk. The capital asset pricing model introduces the idea of a market portfolio. In the KPN framework, all investors are rational and choose the tangency portfolio. In market equilibrium, prices and returns are adjusted so that the supply ratio of assets in the market matches the weights of the tangency portfolio, forming the market portfolio. The problem is that this framework is based on unconditional expected values, with no structural model. Our solution is based on incorporating assets and portfolio dynamics information into portfolio optimization. Exogenous and endogenous information is combined optimally from a geometric perspective. Assuming assets are modeled by unknown partial differential equations with partial derivatives with respect to the drivers that cause their dynamics, drivers optimality with respect to individual assets is defined as being optimal in persistence, the amount of time a driver causes the asset dynamics, and optimal in the probability of causality, the probability of a driver causing the asset dynamics. Specific drivers are defined as the drivers that are optimal for individual assets. We present the commonality principle, which states that optimal drivers for a portfolio, an optimal choice both in terms of persistence and probability of causality for a portfolio, are the specific drivers that are shared the most among all portfolio constituents, or that are repeatedly selected as specific drivers from the greatest number of portfolio constituents. The principle is crucial to our method in that the common causal and persistent properties of these drivers respect portfolio constituents allows us to retain idiosyncratic information at most while projecting them into the space of sensitivities. We now prove the principle first in terms of persistence with model portfolio theory. Drivers contribute to the risk of an asset by causing its dynamics. Specific drivers can contribute to both idiosyncratic and systematic risk in each portfolio constituent, but the amount of systematic risk is not maximal, almost surely. The commonality principle maximizes for each constituent the proportion of systematic risk that is explained by any possible subset of drivers. And the systematic risks are the most persistent as seen in model portfolio theory. Now, the proof in terms of the probability of causality. For the proof, we make use of Reichenbach's 1956 concept of the common cause principle, CCP. Suppose that events A and B are positively probabilistically correlated. Reichenbach's common cause principle says that when such a probabilistic correlation between A and B exists, this is because one of the following causal relationships exists. A is cause of B, B is cause of A, or A and B are both caused by a third factor, C. We check that independent conditions from Reichenbach's common cause principle are met for the common drivers and portfolio constituents in equations 5 to 8, hence the mathematically entailing 9. The common drivers, common cause, can thus be understood to explain the correlation between assets in the portfolio. The generalization of CCP is given by the causal Markov condition, CMC. A variable x is independent of every other variable except x fx and conditional on all its direct causes. CMC can be applied to all pair of portfolio constituents as a generalization of CCP, given the subset of common drivers such that 5 to 8 holds. For that, we need that the common drivers subset is the direct cause of portfolio constituents dynamics, which we approximate with correlation by making use of the CCP for a particular case that the common cause, common drivers is, at most, the same for all portfolio constituents. The extended proof can be seen on the appendix. Now, we focus on the mean variance setup from the model portfolio theory, in which portfolio expected returns is a hyperplane of the constituents, left figure, and portfolio risk is a hypersurface, middle figure. In figure 4, on the right, we can see represented the expected return of the portfolio constituents for a period in the time-dimensional space. We see the axes are timestamps, theta's are angles between expected returns, and the cosines are the correlations. In our setup, the expected portfolio return conditional on the common drivers is a linear combination of constituents expected return conditional on the same drivers. In figure 5, on the left, we see the hypersurface represented and the tangency portfolio we want to reach when solving the portfolio optimization problem. In figure 6, we see portfolio constituents expected returns conditional on common drivers in a time-dimensional space in the middle, like in the previous slide with timestamps as axes, and how we can perform a conformal map into a second space in which the conditional expectations are embedded in the space of sensitivities of constituents with respect to common drivers, the right part of the figure. Here, angles between conditional expected returns are a sum of two components, a systematic component and an idiosyncratic component from the conditional expectation case from model portfolio theory, seen in this previous slide. The conformal map is such that the idiosyncratic component maintains the same proportion between angles in both spaces. We need to show that the embedding of the time-dimensional space into a space of sensitivities with respect to the common drivers is a conformal map. The idea is that if the angle in the mean variance setup between conditional expected returns is a function of both expected returns, which are a function of time too, and the angle can be reduced to a function of time alone, a conformal map implies that the angle in the embedded sensitivity space between the expected returns conditional and common drivers, which is a function of these conditional expectations and time, can be reduced to a function of time alone. The map then is conformal at a given point in time. Case 1 focuses on the case where drivers are not common. In this case, conditional expected returns are orthogonal in the embedded space of sensitivities with respect to drivers' constituents. Not a valid case. Case 2 focuses on common but not causal drivers. In this case, if drivers are not the cause of constituent returns, these are not a function of the drivers. Not valid too. Case 3 is the commonality principle case in which drivers are common, causal, and persistent. In this case, if CD causes constituent returns, these are functions of CD. If and only if those specific drivers are equal common drivers case, the relationship between conditional expected returns is a function of time alone, and the angle in the embedded space is a function of time alone, hence proving the conformal map. With regards to the methodology, common driver selection is performed from a universe of driver candidates, including but not limited to macroeconomic pricing variables, rates, credit, commodities, ETFs, equity indexes, MAR beta, and sector indexes. We rank the correlation for different lags and window lengths and select the top-end common drivers in correlation with respect to all portfolio constituents. Then, on each rebalance period, for each portfolio constituent, we approximate its dynamics with respect to the common drivers with neural networks. In each case, inputs are the common drivers time series returns, target is each portfolio constituent return. We select the optimal architecture for each portfolio constituent based on minimal root mean squared error, i.e. number of units, layers, and lags in time between drivers and portfolio constituents, fitting windows. For each portfolio constituent, expected returns conditional on common drivers are approximated by neural networks, and sensitivities are obtained by automatic differentiation. Then, portfolio constituents are embedded into a space of these sensitivities. Each constituent has as coordinates the average sensitivities of their dynamics with respect to common drivers for the sample period. In figure 7, we see this space and a distance metric between portfolio constituents in orange. Coordinates of the constituents are the sensitivities. The distance matrix between portfolio constituents in this space is called the sensitivity matrix, a distance matrix between the different vectors of sensitivities with respect to the drivers as coordinates. To solve the convex optimization problem for diversification by means of the sensitivity matrix, we cannot use quadratic optimizers. We apply hierarchical clustering to the sensitivity matrix and then leverage two numerical methods from the hierarchical risk parity method by Marcos López de Prado, who applies them to the matrix of hierarchies of a correlation matrix, in contrast to us that we applied to the sensitivity matrix. Hence, our method is called hierarchical sensitivity parity. We ran experiments on two sector diversified portfolios of equities from S&P 500 and Stocks 600. Monthly portfolio rebalances for all cases over a period of 1 year and a half. Optimal drivers are rebalanced, selected every 6 months, and left fixed for the subsequent 6 months. Here, first, we show the performance of the top mean variance method and 1 over n equal weighted, which are very similar. Here we show our method, hierarchical sensitivity parity HSP for different lags, 0 and 1, compared with the hierarchical risk parity HRP and 1 over m methods, and see how performance in terms of ratio is improved by our method. 3.34 for lag 0 for our method versus 2.954 for HRP, hierarchical risk parity. Here we show the same for the Stock 600 portfolio, with our method HSP overperforming all others and HRP in second place. We see our method has a Sharpe ratio of 1.65 versus HRP 1.52 and 1.3 for the top mean variance method. HSP, our method has 34% return in a year and a half versus 22% best mean variance and 30% hierarchical risk parity. To the best of the author's knowledge, it is the first time that is shown that assets and portfolio dynamics can be incorporated via sensitivities into portfolio optimization and approximated with neural networks and automatic differentiation. Also, that portfolio constituents are embedded into a space of sensitivities with respect to common drivers, and the sensitivity matrix allows to solve the convex optimization for diversification. Also, the commonality principle allows for the conformal map between spaces to keep maximum idiosyncratic plus systematic risk representation in the embedded space of sensitivities, allowing the hierarchies of the sensitivity matrix to retain both sources of diversification, in contrast to the hierarchies of the correlation matrix in hierarchical risk parity. This explains overperformance of our method with respect to the rest of the out-of-sample methods. For future work, it would be interesting to apply other neural network architectures such as recurrent neural networks, also to use SDEs instead of PDEs to model the dynamics and approximate them with neural networks. Finally, to apply the commonality principle to Bayesian network solutions.